All right, welcome back everyone to the deep dive. You know how this works. We take a really cool machine learning paper and we break it down.
Yep. This time around, we're looking at image classification. Specifically, how to make it even better with this thing called a mixture of experts. It's kind of like, well, we'll get into that.
Right, a mixture of experts, or MoE. It's like having a whole bunch of specialized AI models working together instead of just one model trying to do it all. But making that actually work well, that's the tricky part. This paper we're looking at today, they found a really interesting way to train these MoE models, especially when the data is messy, which, let's be real, data is always a little messy.
Yeah, noisy data, outliers, those are the things that can really trip up your typical model. This paper calls their new approach the double-stage feature-level clustering and pseudo-labeling-based mixture of experts framework.
Wow, that's a mouthful. DFCPMoE, maybe?
Yeah, DFCPMoE, that's way easier. Basically, it's all about using the data itself to help guide those expert models to figure out what each one should specialize in.
So before we even start training the MoE, we're kind of like pre-sorting the data.
Exactly. Think of it like this. You wouldn't throw a complex project at a team and just say, figure it out.
Yeah.
You'd want to see who's got what skills and assign tasks accordingly.
Makes sense. So how does that work in practice? Walk us through the steps of this DFCPMoE thing.
Okay, first step is feature extraction. We got to take those raw images and turn them into something the model can understand. Numbers, basically, like a set of descriptors for each image.
Ah, so it's not training on the pixels directly. It's like extracting the important visual info first.
Right. And for this, they use a pre-trained EfficientNet model, which is already really good at recognizing visual features like edges and textures and stuff.
Oh, that's smart. Leveraging an already trained model to kind of jumpstart the process.
Exactly. They basically chop off the classification part of that EfficientNet and just use the good stuff, the features. So they've got these features. Step 2 is where the double-stage clustering comes in.
Okay, so clustering, that's like grouping similar things together, right?
Right. First, they use a pretty standard algorithm called k-means to make these initial clusters. It tries to group images based on how similar their features are.
So like all the pictures of cats in one cluster, dogs in another, that kind of thing.
Yeah, kind of like that. But those initial clusters, not perfect. They use this thing called the Davies-Bouldin index to measure how well the clusters are separated. And a high score there means things are kind of jumbled up.
Oh, so it's like you've got some cats and dogs mixed together and the clusters themselves aren't that distinct.
Yeah, exactly. So that's where the double stage part comes in. They do a second round of clustering using this k-nearest neighbor approach. It basically looks at each image and compares it to the central image in each cluster. And if it's more similar to a different cluster, it gets moved.
Oh, interesting. So the second stage is like a refinement process.
Yeah.
Making those clusters a lot more, well, pure.
Yep. They use this threshold based on distances between images to decide when to move things around. And through experimentation, they found that a threshold of Bro 8 works really well for this.
Okay, so now we've got these well-defined clusters of images, but they're still unlabeled, right? We don't know if the cluster's cats or dogs or what. So how do we actually use these for training our MoE?
That's where the really cool part comes in, the pseudo-labeling. They take a small set of images that are already labeled, and they use those to train a special kind of neural network.
What kind of network?
It's called a Siamese neural network, and it's really good at comparing two things and figuring out how similar they are.
Siamese network. So like
Right.
You give it two pictures of cats, it says, yeah, those are similar.
Right. And if you give it a cat and a dog, it says, nope, different. And they train the Siamese network using a specific type of loss function, a contractive loss. That helps it get really good at separating similar things from different things.
Okay, I think I'm following. So they use this trained Siamese network to look at the images in those unlabeled clusters and compare them to the labeled images. And based on that comparison, they make an educated guess about what the unlabeled images are.
Exactly. That guess is the pseudo-label. And they're not just guessing randomly. They use a measure called the F1 score to figure out the best threshold for applying those pseudo-labels. So they're only applying them when the Siamese network is really confident.
Smart. So essentially, they're taking a small amount of labeled data and using it to label a much larger set of unlabeled data. That's super efficient.
Right. Now, finally, we get to the MoE part. Remember, on MoE is like a team of experts. In this case, each expert is a neural network trained to recognize certain types of images. And there's this managing network that decides which expert gets assigned to each image.
And since we've already pseudo-labeled our clusters, we can train the managing network to send specific clusters to specific experts.
Right, you got it. So, for example, the managing network learns to send all the cat clusters to the expert that's really good at recognizing cats. And because we've pre-clustered the data, each expert can focus on getting really good at its assigned task. It doesn't have to worry about all the other stuff.
That's clever. And that solves the problem of some experts dominating the training early on.
Exactly. It's like giving everyone clearly defined roles. And then when we actually use this trained MoE, the managing network looks at the features of a new image and decides how much each expert should contribute to the final classification.
So it's a weighted average based on the expertise of each model.
Awesome. Okay, we've covered a lot of ground here, but let's step back for a second. Why is this DFCPMoE approach so important? What are the limitations it's trying to overcome?
Well, using multiple models to solve a problem isn't a new idea. Think of traditional ensemble methods like bagging or boosting. You train a bunch of models and combine their predictions. But those methods don't really allow for this level of specialization.
Yeah, it's like comparing a team of general practitioners to a team of specialists.
Exactly. Early MoE models often use simpler machine learning models as the experts, like decision trees. But those models just weren't as powerful as the deep neural networks we use today.
Right, deep learning has really changed the game, big time. The breakthroughs in MoE came when people started using deep learning for those expert models. And they came up with ways to only activate a small subset of experts for each input, to make training faster and more stable. But this clustering and pseudo-labeling approach, that seems to be a more effective and robust way to get those experts specialized.
Okay, so let's dig into some specifics of how they implemented this DFCPMoE. They used a pre-trained EfficientNet B1 model for feature extraction. Why choose that particular model?
Well, EfficientNet is known for being really efficient, hence the name. It gets really good accuracy on image classification without using a ton of computing power. And it's pre-trained on this massive data set called ImageNet. So it's already learned a lot about visual features, and that gives us a head start. We don't have to teach the model everything from scratch.
Gotcha. And they specifically removed the last layer of that EfficientNet and avoid pooling operations. Why is that important?
That's to preserve the spatial information in the image, the relationship between different parts of the image, which is important for clustering later on.
Makes sense. And that double stage clustering, that seems super important. What's the real benefit of that second stage, the one with the k nearest neighbor rule?
It basically cleans up the initial clusters. The k-means algorithm can be sensitive to outliers and noise, and that second stage helps refine those clusters, making them more pure, so the groups are more representative of the actual underlying similarities in the data.
Okay. And the pseudo-labeling with that Siamese network, they use that contractive loss function to train it. Can you unpack that a bit?
Sure. The contractive loss forces the Siamese network to learn how to create these embeddings of images. And in these embeddings, similar images are close together and dissimilar images are far apart. It's all about learning a good measure of visual similarity. And that allows them to use the trained Siamese network to reliably guess the labels for those unlabeled clustered images.
Awesome. Okay, last piece of the puzzle. Let's talk about how that managing network learns to do its job during training. Sending the right images to the right experts.
Right. So during training, the managing network learns to assign weights to each expert. Like how much should each expert contribute to the classification of this image? And since the data is pre-clustered and pseudo-labeled, the managing network learns to send images from a particular cluster to the expert that specializes in that type of image.
And if it messes up, if it sends images from the same cluster to different experts, there's a penalty during training.
Right, exactly. And that encourages the whole system to specialize effectively. And that's key for the whole DFCPMoE framework to work.
Okay, cool. So they tested all this out on the GTSRB dataset, which is all about traffic signs. What did they find?
The results are really good. They found that over 95% of those expert models were actually contributing significantly to their assigned classes, which shows that specialization was working. And the purity of those clusters after pseudo-labeling was super high, like 98%. So their clustering and labeling process was doing its job.
And how did it compare to a regular MoE and a standard dense network?
The DFCPMoE beat both of them in terms of accuracy. It got a mean average precision of 99.95% and a balanced accuracy of 0.99, which is super impressive.
Wow, almost perfect.
Yeah, and it wasn't just more accurate, it was actually faster, too. The average inference time was only about 51 milliseconds.
Wait, faster? How is that possible? It seems like having all these experts would make things slower.
They do this clever thing where they pre-compute the first few layers of all the expert models in parallel. So when a new image comes in, a lot of the work is already done, which speeds things up.
Oh, that's clever.
Yeah.
But the training time for the DFCPMoE was much longer than for the dense model, right? Like 126 hours.
Yeah, training a system this complex does take more time. You've got all those expert models and the managing network and all that pre-processing. But it's interesting that the DFCPMoE actually trained a bit faster than a traditional MoE, probably because that pre-processing makes the training more focused and efficient.
Right, so you pay a little upfront cost in terms of training time, but you get a huge benefit in terms of accuracy and speed later on.
Exactly. It really shows the power of understanding the data before you jump into training.
All right, now for the novel notions segment, where we think about how to push this research even further. What are some interesting directions we could go from here?
Well, this whole framework seems super promising for images. But what about other types of data? Like, what about video?
Ooh, yeah, video is way more complex than just static images.
Right. You've got that temporal dimension to deal with. But what if you could cluster video clips based on the actions or events happening, and then have MoE experts specialized in recognizing different types of events? That would be huge for things like self-driving cars.
I love that idea. You could even use a small set of labeled video clips for pseudo-labeling. It would be super challenging, but the potential payoff is huge.
Totally. And here's another thought. Remember how they use that small labeled dataset for pseudo-labeling? What if we could make that even more efficient? By using active learning. Instead of just having a fixed set of labeled data, the model could actively request labels for the most informative, unlabeled examples, like the ones it's most uncertain about, or the ones that are most representative of a cluster.
Well, that's interesting. So it's like the model is saying, hey, I need more information about this specific type of image. And then it gets a label for that, and the whole system gets better.
Right. And you could even imagine having a human annotator in the loop. So the model asks for a label, a human provides it, and that feedback helps refine the whole process.
Those are some really cool directions. It seems like this DFCPMoE could be a springboard for a whole bunch of new research.
Definitely. And for our listeners who want to dive deeper, we've got a link to the full paper in the episode description.
Awesome. Well, that was a deep dive. Thanks for joining us. We hope you learned something new about mixture of experts and the future of image classification.
And we'll be back soon with another deep dive into the fascinating world of machine learning research.
See you next time.